Alright guys, this is video 1.3.2, so the second half of our 1.3 notes, and we're going to do 3 sample problems here. Alright, so the first one. Here's our first reaction. We have sodium carbonate, that's aqueous, calcium chloride, aqueous, our calcium carbonate solid, and our sodium chloride, that's aqueous. And this of course is the same reaction we've been dealing with before. So a 100 ml sample of calcium chloride is titrated to the equivalence point. So that means like to the end point, with 50 milliliters of 0.2 molar sodium carbonate solution. What's the concentration of the original calcium chloride solution? So one thing that we are going to make sure we remind ourselves of is the units of molarity, units of concentration. So up here, unless noted, and this is always in these problems, so unless noted, all concentrations are molar. And to remind ourselves what molar is, so molar is that capital M, and that means moles of solute over liters of solution. So it could be 1 liter or 1,000 milliliters. It doesn't matter. Okay, so for our first one here, the first thing we're going to do is we are going to start with our moles of carbonate, or CO3 solution, because that's what we know. So we know the amount, we know the concentration, so we could figure out how many moles of this we added. So this is a source of carbonate ions. So our CO3 2- ions. So Na2, or Na plus, there's 2 of those, and 1 carbonate ion. So that's our source of carbonate. So to figure that out, first we're going to start with how much we added. So we added 50 milliliters of our carbonate. And of course that was here, our 50 milliliters of our carbonate. And we have the concentration, so we can figure out moles. It's a 0.2 molar solution. So that means that we've added 0.20 moles of carbonate per liter, or 1,000 milliliters, same thing. And we don't really care about the carbonate here. We're caring about the concentration of the calcium chloride. So we need to go to the moles of calcium here. So I'm going to use my mole ratio in our balanced chemical equation, our sodium carbonate and our calcium chloride, to look at the ratio between our carbonate and our calcium. So this is a 1-to-1. There's an imaginary 1 there, imaginary 1 there. So for every 1 mole of CO3 2-, you need 1 mole of Ca2+. And plugging this into your calculator, you should get 0.0100 moles of calcium. I encourage you to please type that in. Make sure you got it right. Make sure you know how to use your calculator, so that way when you get to the test, nothing goes wrong. Okay, so it doesn't ask us about the number of moles of calcium, it's asking us the concentration. So make sure you always go back, make sure you read exactly what you're trying to find here, so you end up finding the correct thing. So the concentration of calcium ions, these little brackets mean concentration, they mean molarity, equals, now if this is molarity, it's going to be moles per liter. So we have our moles that we calculated here, 0.0100 moles of calcium over the total volume, so the liters of our solution. And in this case, our overall amount of solution was 100 milliliters. But this is in moles per liter, so I'm going to write this in liters, which is 0.100 liters of solution. And so you should go ahead and plug this into your calculator and get 0.100 molar Ca2+. And that's your final answer there. Alright, moving on to part B of this problem. When 50 milliliters of 0.2 molar sodium carbonate solution is added to 100 mils of calcium chloride, we get a precipitate. We get 0.855 grams of precipitate was collected. So we know that our precipitate is going to be calcium carbonate here. That's the only solid that's formed. So what's the concentration of the original calcium chloride in the solution? Okay, so we're going to start with the amount of precipitate that we got out of solution. and we're going to work backwards. So we start with 0.855 grams of our precipitate, which we know from our equation is calcium carbonate, CaCO3. Alright, so let's get that into moles. So use the periodic table, find the molar mass. So 1 mole of calcium carbonate is equal to 100.09 grams calcium carbonate. And of course, we don't care about the calcium carbonate, we care about the original calcium chloride solution. So I'm going to go ahead and look at my number of moles of my calcium ions. So 1 mole of CaCO3 has how many moles of calcium in it? Well, that's just 1 mole of calcium. So 1 mole Ca2+. And that gives me moles of calcium. Plug this into your calculator, you should get 0.00854 moles of Ca2+. Now, of course, it's asking us concentration, so we have to do our moles per liter equation again. Ca2+ equals 0.00854 moles of Ca2+. For our overall volume of solution, we had 100 milliliters here, so that would be 0.100 liters of solution. Plug this into your calculator, and you should get 0.085 molar. And that's the concentration of our calcium ions, which is the same as our calcium chloride solution here. So molar calcium chloride. Okay. Next problem. Consider your reaction here. So here's our solid. This is a liquid right here, so those ones are not going to be dissociated. Calculate the volume of CO2 gas generated when 0.350 grams is added to the excess. Okay, so at STP. So you know at STP you can use that 22.4 liters per mole. So can use 22.4 liters of gas per mole of gas. Alright, so knowing that, let's go ahead and work backwards. So we're given that we used 0.350 grams of NaHCO3. So I'm going to go ahead and start with that. 0.350 grams NaHCO3. And of course we need to get into moles to really do anything here. So use your periodic table and find the molar mass. 84.008 grams is equivalent to 1 mole. And remember, try to keep all those digits there. Okay, of course, we care about moles of CO2, so we need to get into moles of CO2. So looking at my balanced equation, well, this one's pretty easy. There's a 1 there, and there's going to be a 1 over here at my CO2, so it's going to be a 1-to-1 ratio. Still write it in, even though it's 1-to-1. It doesn't really affect your math. Still write it in. HCO3. Okay, and it doesn't care about moles of CO2, it wants us to find liters, or volume of CO2. And since we know that this is at STP, we can go ahead and use our conversion factor and make this nice and easy. We know that 1 mole of CO2 gas at STP is equal to 22.4 liters of CO2. Plug this into your calculator, you should get 0.0933 liters of CO2 gas. Okay, so remember, this was only a short stoichiometry problem because we were at STP. So if we look at part B, however, we're at 30 degrees Celsius and 700 torr. That's not STP. So in this case, we need to use the ideal gas law, PV equals nRT. Well, we know when we use the ideal gas law, we're going to need that N term, which is the number of moles. And we're concerned about the number of moles of gas here formed, so the number of moles of CO2. So let's go ahead and find that. So we can use our stoichiometry all the way up to this point that we used before here, and we can get moles of CO2. So I'm just going to go ahead and rewrite that. 0.350 grams convert to moles. And we know this is a 1-to-1 ratio. So 1 mole of CO2 Okay, plugging this into your calculator, you should get the number of moles of CO2 coming out to 0.00417 moles of CO2. Alright, so we just did that ahead of time because we know we're going to have to plug it into the ideal gas law. So PV equals nRT. I rearrange it first. V for volume, we're trying to find volume, of course, equals nRT over P. So let's go ahead and plug everything in. So we just calculated N, our number of moles here. So we have 0.00417 moles. And so that was from up here. We calculated that number of moles. The R term here is your ideal gas constant. And this is at the back of your periodic table, if you don't remember it. 0.0821 liters times atmospheres times inverse moles times inverse kelvins. And then our T is our temperature. Well, that's 30 degrees Celsius. So 30 plus 273 K, so it's going to be our Kelvin temperature there, divided by our P for pressure, and we know we need to cancel out atmospheres, so it needs to be in atmospheres. Right now it is in torr, so 700 torr times 1 atmosphere over 760 torr. If you'd like to convert this off to the side and then plug it in, that's completely fine too. So at this point, I would like you to please pause the video and try canceling all the units here, show where all the units cancel, and plug it into your calculator and put down your answer. Okay, so you should have gotten 0.113 liters of CO2 with sig figs here. We're at 30 degrees Celsius and 700 torr. There's only one sig fig, so with sig figs you should have 0.1 liters of CO2 as your answer. Alright guys, number 8, so last one. A 100 ml sample of 1 molar, let's see, that's potassium phosphate, is mixed with 100 ml of 1 molar silver nitrate forms a precipitate. Alright, list the ions that remain in solution in increasing concentration. Okay, so first thing I'm going to do is I'm going to figure out how many moles of each I have here. Because you can't really work with volume, you can't really work with molarities, so we're going to go ahead and convert to moles. So moles of our K3PO4, we had 0.100 liters of it times its concentration, 1 molar. So 1 mole K3PO4 over 1 liter, so liters cancel out, and you end up in 0.100 moles K3PO4. We're going to do the same thing for our silver nitrate. So you guys go ahead and pause the video and you figure out the moles of silver nitrate. Okay, you're starting with your 0.100 liters. Multiply this by its concentration, 1 liter, and you end up with the same number of moles. So that makes it nice and easy to do our calculations later. Okay, next thing you're going to do is you are going to write a balanced chemical equation for this. You have to write a balanced chemical equation. And how do you know which one forms a precipitate? Well, the answer is that you have to memorize those solubility rules. So your solubility rules are going to tell you what's soluble, what's not. Okay, so our K3PO4, it's our first reactant, and we know that that's soluble, so that's going to be aqueous. Plus our silver nitrate, AgNO3, that's soluble, it's going to be aqueous. Yields, so let's see, this is going to be a double replacement reaction. So the potassium, I'm just going to show you very quickly how we do this. The potassium is positive, silver is positive. Our phosphate, of course you memorized that, that is negatively charged. Our nitrate is negatively charged, so positives and negatives are going to switch places. So you're going to have your potassium go with your nitrate, and your silver go with your phosphate here. So let's go ahead and write that out. So silver, Ag, is going to be with PO4. So PO4 has a charge of 3 minus, silver's plus 1. So we need 3 silvers there. And this is insoluble in water, so this is your solid. Plus your K, NO3. So you're going to end up with K, NO3, plus 1 minus 1 charge, so we don't need 3 there. This is going to be aqueous. Of course, we know that from our solubility rules. Going back and balancing, we should have a 3 there. We should have a 3 there. Okay, so we are going to do a table like we initially did in our other notes at the beginning of the last video. So we're going to do a table kind of like, let me grab that, kind of like this. So the initial, change, and final. Instead of final, I'm going to write E for ending and call it an ICE table. So I, C, E. Okay, so this is our initial amounts here. So initially we calculated already that we added 0.1 moles, 0.100 moles, and so these are all going to be moles, so I'm not going to write mole after everything. 0.100 moles were initially added of each of these. And initially, before the reaction goes, we don't form any products. As the reaction goes, actually I want you guys to go ahead and pause it. So these two are going to be subtracted. How much do you lose? How much do you gain of each one? You go ahead and try. Okay, so if you got minus 0.033 and minus 0.100, you would be correct. And so that means that you need only a third of this for every one of these. Or you would need 3 of these for every one of those. Sorry, 3 of these for every one of those. Okay, so plus 0.033 plus 0.100. And then for your ending amounts, you're going to go ahead and add these up. So E for end, you can also do F for final. So here you end up with 0.067 moles. For this compound, you end up with nothing, so 0 moles. Here you end up with 0.033 moles. And finally here you end up with 0.100 moles. So you just add them up and those are your finals. These numbers are going to be the ones that we are concerned with here. So now if we look back at our question, it's asking us to list the individual ions in the solution in increasing concentration. So let's look at how many ions are here. Oh, this is a source of K plus ions. So there's some K plus ions there. And phosphate ions. So PO4, 3 minus. This one is a source of silver and NO3. Of course, we don't have any of those. There are no ions here, and that's because we have a solid, so there are no free ions. This is just a neutral solid. Here, this is going to be a source of your potassium ions and your nitrate anions. Okay, so let's look at our potassium ions, K+. So K+, we're going to have 3 of those in our K3. So we have 3 potassiums, and that 3 is just from the balanced equation here. So we have 3 at this concentration each. So 0.067. Okay, do we have potassium ions anywhere else? Oh, yep. We have potassium ions here. We have 3 of them at this concentration, or at this molarity, or this number of moles. So plus 3 of them at 0.100. And that gives us a total of 0.500 moles of that. Phosphate. Please pause the video, and I want you to figure out the number of moles of phosphate ions that you have in solution. Okay, so here's a phosphate, and here there's only one phosphate, so 1 times 0.067. Any other sources of phosphate? Nope. So our final number is 0.067 moles. Okay, our silver and our nitrate. Please pause the video and figure out the number of ions of silver in nitrate. Okay, we're back. So let's see, silver. Okay, right here I would have 3 silvers. So 3 times, well, you don't even have to really write anything because there's 0. And there are no other sources of silver because notice our silver here is bound up in our solid, so we can't use that as a free ion. So that's going to be 0 moles of silver. Our nitrate, let's look for our nitrates. There's a source of nitrate. There's only one of them in the compound, so 1 nitrate times, let's see, 0. Oh wait, I'm sorry, that's wrong. There are 3 nitrates there. So that 3 applies to the silver and the nitrate. My mistake. So 3 times 0 plus, let's see, are there any other nitrates? There's 1 there. How many nitrates? Well, same thing as before. We're going to have 3 of them. So 3 at 0.1 each. And that's going to go ahead and give us 0.300 moles. Okay, so that's the total number of ions that are floating around in our solution. And it asks us, let's see, list the ions in increasing concentration. Okay, so in increasing concentration, the one we have the least of, it's going to be silver. So that's Ag+, followed closely by phosphate, O4 3-, followed next by our nitrate, NO3-, and then there's the most of the potassium ions in solution. So this would be what your final answer would be, and all of this above would be the work to support it. All right, that is the end of lesson 1.3.